So our first speaker this afternoon is Stephen Sharpe, and he will tell us about multi-particle scattering amplitudes from lattice QCD.
Okay, thank you very much. It's a real pleasure to be here. I thank the organizers for inviting me to come from a different field and my first time ever at Amplitudes. Very interesting. This will be very lowbrow compared to what you heard this morning, but hopefully interesting and perhaps surprising. In fact, if you know anything about lattice QCD, we work in Euclidean time and in finite volumes. So, what do we have to do with amplitudes, infinite volume, Minkowski time quantities? Well, you'll see. I hope to convince you that it's possible to do that. My real title will be three particle scattering amplitudes from lattice QCD. That's the frontier of the present calculations, even though I'll talk about two particle scattering amplitudes along the way. So 3 to 3. I want to mention at the beginning my collaborators. I'm going to describe work which has taken place over more than the last decade, involving a bunch of students at the University of Washington elsewhere and other collaborators. And this work would not have been possible without these folks, some of whom you may know. And I should also mention that in this area of lattice QCD, there are other things you can do. You can calculate current matrix elements between multi-particle states. I'm not going to mention that at all. That work is being led by Max and Raul and Fernando. So look out for that. Okay, now, perhaps I don't need to motivate the calculation of amplitudes at this conference, but from a lattice point of view, as you'll see, it's a lot of work, so why are we doing it? And I'm going to give you three motivations. The first is that we would like to determine the properties of strong interaction resonances from first principles, from QCD. For example, exotics such as the doubly charged tetraquark. And you may know that over the last decade, there have been a huge number of additional hadrons observed. This is at the LHC, a lot of them at LHCb. This guy is the doubly charged tetraquark, but there's X's and Y's and Z's. These are particles which do not fit into the standard quark model view of hadrons. We would like to understand what their properties are, both because we want to understand QCD, but also because it teaches us about what can happen in strongly interacting theories in general. A second motivation is to determine from first principles the three-body interaction between, for example, three neutrons, or three pions, three kaons, you listed, but three neutrons are important for understanding. The three-neutron interaction is very important for understanding the equation of state of neutron stars, for instance. And it's not pinned down well from nuclear physics. And finally, this is actually my personal major motivation, and I won't be talking about this today, but I want to just say it, that related to the calculation of scattering amplitudes is the calculation of decay amplitudes within the standard model, electroweak decay amplitudes, such as k to pi pi, or k to 3 pi, or d decays. These are all picked because in these processes, there is observed or almost observed CP violation. That's something which is predicted in the standard model in terms of one parameter, the phase delta. And we would like to know whether the prediction of the standard model agrees with the experimental results. And for k to 2 pi, this is almost done now. But for the d decays, I don't even know how to do it theoretically. And so the work I'm doing is aiming towards that in the long run. I won't say any more about that, though, today. Okay, so I'm going to focus on the 3 pion amplitude for most of the time. Okay, that brings me to my outline. So I want to begin with this issue that I already raised. How can you get scattering amplitudes from finite boxes in Euclidean time? So I want to state it more clearly and then sketch how we resolve it. And then the rest, that involves certain formalism. I can't really derive that formalism for you in the three-particle case, but I can derive it for you, at least a sketch of it in the two-particle case, so you can see the inputs that we use. So this part here is formalism. And then I hope to get to some examples of the status of applications where we actually take lattice QCD data, push it through this formalism and get out scattering amplitudes. And then the last of these is preliminary results, hot off the press for 3 pi pluses to 3 pi pluses at essentially physical quark masses that we can do now. And I will not have time to talk about the tetraquark. I ran through this last night, and there's no way. That's a large number. We'll see how I go. All right, the fundamental issue. So if you stay awake for anything, stay awake for this bit, and maybe wake up at the end when we get to this, some pretty pictures of results. Okay, so what do we do on the lattice? We calculate correlation functions in finite volumes in Euclidean time. So here's an example of a correlation function. We have an operator which creates 3 pions, so that's 3 antiquarks and 3 quarks in some fashion in a color singlet form, and we destroy it at a later Euclidean time. We can project it onto definite momentum. I'm going to assume a cubic box with periodic boundary conditions, so the momenta are quantized like so. So we pick one of those values, and then, so that's what we calculate. And I'm not going to talk at all about how we do that. Supercomputers, many years, algorithms, blah, blah, blah. Okay, my collaborators give me the answers from this. I actually am not doing this myself anymore. What does that tell us? So if we insert e to the minus ht, h tau, what we find is that this gives a sum over intermediate states. These states are the states with the quantum numbers of whatever operator we put in this case 3 pions, say 3 pi pluses, some fixed momentum, and other quantum numbers related to angular momentum. But we're in a cubic box, so we don't have all angular momentum. We just have a subgroup, the cubic group. So the states are labeled by that, and you'll see that later. And then for each set of quantum numbers, we have a tower of states. And we can measure these matrix elements, or their square, and most importantly, we can measure the energies. Now, those are physical quantities. That's the good news. They're not the physical quantities we want, but they are physical quantities. And the state of the art is that for each choice of quantum numbers, we can get 5 to 10 levels using various methods. I won't go into that. We're now approaching physical quark masses in the calculation of these. Of course, these results come with errors, statistical errors, because it's a Monte Carlo method, systematic errors. For example, we need to take the lattice spacing to 0. So there always will be errors. I'm not going into that today. I'm just assuming that my collaborators, have provided me with these energies. Okay, so that's what we get, finite volume energies. And of course, that's neither Euclidean or Minkowski. Those are just the energies of states in finite volume. They're completely well-defined physical quantities. But this is what we want, scattering amplitudes within states and out states, which are infinite volume objects. So the issue is how to relate these two. And this relation is a finite volume quantum field theory problem, and that's the problem that we've been addressing. And I'm going to skip over this because I don't have time. This is the method that I'm going to explain. So this is how we found out that we can resolve this problem. And it involves 2 steps. Okay, so we take the spectra, say, for example, for 2 pi pluses and 3 pi pluses. Those are 2 separate spectra because in the isospin symmetric limit, 2 and 3 pions don't mix. And we have derived quantization conditions. So these are secular equations you can see here. They involve, in this case, a kinematic function, which I'll talk a bit about later. Depends upon the kinematics of the box, the shape of the box, the size of the box. And that's a finite volume quantity, and infinite volume quantities, K matrices. So K2 is simply the sum of all Feynman diagrams for 2 to 2 scattering, except you use the principal value prescription instead of the I epsilon prescription. So it's related to M2, but it's a real smooth quantity and it has no unitary cuts in it. And if you have to truncate in angular momentum to make this otherwise infinite matrix equation useful, but when you've done that, you can solve this equation. Given K2, you can predict the 2-particle spectrum in your box. And so what you do in practice is you parameterize K2 with some parameters, which you then fit to the data. Okay, that was sort of old news. That was derived in the late 80s. But what we derived in the last 10 years are results of this form for 3 particles, which look similar. And they involve a 3-particle K-matrix, which has DF, which stands for divergence-free, which I'll get to later. But it's an infinite volume K-matrix, but it's also unphysical. It has the same symmetries as M3, but it's real, has no unitary cuts, but it is unphysical because it involves a cutoff function, which I'll mention later. Nevertheless, this is completely well defined. So we parameterize this KDF. I'll talk about what F3 is later, but we know what they are. We choose the parameters such that we match the spectrum, and then we extract these quantities. That's step 1. Step 2 is we input these quantities into some integral equations that we have derived, which the output of which is the scattering amplitude. And these integral equations put back in the final state interactions. They ensure that this scattering amplitude is unitary, S channel unitarity. And if we've parameterized the K matrices in some analytic way, when we solve these integral equations, we can do so not only for real momenta, but also for complex momenta, and look for poles, bound states, and that's what we're doing. So that's the take-home of this method. So now let me explain to you how we get these formulae, at least in the 2-particle case. So this was done originally by Martin Luce, using some very clever techniques, which are not too simple, but later on, Chris Kreider, Changwan Kim, and I derived a simpler approach, which I'm going to follow, and actually I simplified it even further. Okay, so the starting point looks very similar to what I had before, except I have 2 pions, 2-pion operator here, but also now I am in I'm going to put myself in Minkowski time because I'm doing things formally. I don't need to actually do any numerical calculations. So this is the Fourier transform. This is a finite volume Minkowski correlation function, Fourier transform to energy and momentum space. And when you have an intermediate state, that leads to a pole in this quantity. So we're looking for poles in this quantity. That tells us the finite volume spectrum. Okay, and the framework we're going to work in is a generic effective field theory for whatever particles are the relevant ones, in this case, pions, and possibly kaons. We do not need to know anything about that effective theory other than we assume it exists, and we work to all orders. We'll also use time-ordered perturbation theory rather than regular perturbation theory because that simplifies some of the arguments, but it's not essential. And as I said before, I'm going to assume exact isospin symmetry in this discussion, so the 2 pions can only go to 4 pions, not 3 pions. A key point is that we have to restrict the kinematic range. The center of, this is correct. The center of mass energy must lie in this range. In particular, it cannot go above 4m pi, because then the intermediate states could include on-shell 4 pions. And we do not know yet how to incorporate that. So the point of this constraint is that the only intermediate states that contribute which can go on shell are 2 pions. Okay, so we start writing down diagrams. Okay, here are the simplest diagrams. This green box represents this creation operator, the red box the destruction operator. I'm inserting this energy and momentum here, and I'm using an on-shell subtraction scheme such that this propagator has its pole at the physical mass. If I do so and I work out time-ordered perturbation theory, then I know that I get these intermediate energy denominators, which in this simple case is just the difference between the input energy and the energies, the on-shell energies of these 2 particles. Okay, note that I don't need an I epsilon. I'm in finite volume. I don't hit the poles. Another diagram is I just reverse the time ordering. That corresponds to flipping the sign of E. For this set of this constraint, this can never go on shell. And then I have higher order diagrams. Again, these can go on shell. And key point, of course, is even though I'm working in finite volume, these vertices, short distance vertices, remain infinite volume. And here's some more diagrams with various time orderings. And you can have, in my generic theory, I can have any number of particles coming out of the vertices. Could be 6, could be 8, whatever. But the key point is that these red dashed lines correspond to intermediate states, E minus 4 omega in this case, which can never go on shell for my range of energies. So they're non-singular, whereas the purple ones can go on shell. Okay, so I imagine an infinite series of diagrams of this form. These vertices can have derivatives, whatever. There's no constraint. So I divide my cuts into what I call relevant, the purple, and irrelevant. And I remind you that we're working in finite volume, so in the loops, all these momenta are summed over the finite volume set, not integrated. Okay, so what do? The mantra is we want to replace as much as possible finite volume sums with infinite volume integrals, because we want to relate things back to infinite volume quantities. So we use the Poisson summation formula, which you're very well familiar with, I'm sure, and we note that the difference between the sum and the integral, this term here, involves Fourier transforms, and if our function g, our integrand in those loops, is smooth with derivatives of order scaling with m pi, then this leads to contributions which are exponentially suppressed. Okay, they're of the form e to the minus m pi l, or some square of that, and those we will drop. Okay, that's the accuracy that we're working to. Thus, we have to make sure that we're in boxes large enough that m pi l is large enough that e to the minus m pi l is small enough. And in practice, m pi l of order 4 means percent level corrections, and for present work, that's good enough. Okay, so using this and dropping these corrections allows us to replace the momentum sums in cases like this, where there is no singularity, with integrals up to these corrections. But we can't do that in the two-particle case because there is a singularity, and I've been assuming the absence of a singularity. So what this allows us to do is to sum up all these irrelevant cuts into beta-salpeter kernels and corresponding end caps. So here, the end caps will play no role, so I'm not really talking about them. But the beta-salpeter kernel is, two-particle irreducible in the S channel. It's the infinite sum of diagrams where I have more than 2 particles in the intermediate states, and I integrate them. So that's an infinite volume quantity. And this is the time-ordered perturbation theory beta-salpeter kernel. And when I resum and collect things in terms of the number of relevant cuts, my correlator takes this form, where this first term is just where everything is an integral. Okay, so I've dealt with that. The second step is, what do I do with these relevant cuts? Okay, so here's an example of a relevant cut. I have something on the left, something on the right, and then I have my energy denominator and the usual propagator factors. Okay, so what I do is I replace the sum with an integral, principal value regulated integral over the pole, plus a difference between the sum and the integral. So I do something trivial. But the key point is, so my mantra is I want to replace sums with integrals, but here I get something left over which I can't throw away. It is not exponentially suppressed because the integrand has a pole. Okay, but what I can do is I can set the functions to either side of this on shell, because the difference between the on and off shell comes with a factor of e minus omegas, and that cancels the pole, and the sum integral difference is then exponentially suppressed. So I can use this new type of finite volume cut to set my beta-salpeter kernels on shell, and I do it in a particular way. I go to the center of mass frame, I project onto angular momenta, and then I go on shell. I'm not going into the details, but that's a convenient way. That's convenient because we know that as you go to higher energies, the amplitudes get smaller as you go to higher L. Okay, so what you can show is that this equation is this is an identity up to exponentially suppressed corrections. Sum equals integral plus sum integral difference, where I project on shell, and this sum integral difference has this particular form. This is a function you can just calculate. This is my f. Okay, so this is just the key move in this analysis. You replace this sum with an integral plus this f, which sets things on shell. So let me now proceed to complete the argument. This is what we had before. I now replace all the sums with integral plus f cut. And now I just do a standard reorganization. I collect terms with 0 f cuts, 1 f cut, 2 f cut, and so on. Okay, so, and when I do so, I change to a matrix basis where the matrix indices are L and M, the angular momentum in the center of mass frame. So I've now written these as matrix multiplies. So this, what appears here is in between these F's here is B2 plus B2 integral B2 plus etc. It's another geometric sum there. And that indeed is what turns a beta salpeter kernel into a K matrix. Anyway, for now, that's our definition. And something similar happens for the n caps. So I end up with this expression here, which is a geometric series. And I just sum it. And that's my final result. And let me put this on the next slide and look at it. Remember, I'm looking for the poles in this quantity because they tell me the finite volume spectrum. Those poles, the energies of those poles must depend upon L, its finite volume. So this first term, which is an infinite volume quantity, is not relevant. Maybe it has cuts in it, but it's not relevant for poles. The poles will come from this second term. And this is a matrix. When the eigenvalues of this matrix down below go to 0, that's where I get my poles. So the quantization condition thus becomes the determinant. I can move this f downstairs, and then I get this expression that I showed you before. So that is how I derive this two-particle quantization condition. And I want you to appreciate that this is a very beautiful result because it factorizes the finite volume kinematics from the infinite volume physics. This is an infinite volume quantity. This is a purely kinematical finite volume quantity. K2, because it's infinite volume, angular momentum is conserved, so it's diagonal in L and M. F, on the other hand, it comes related to the box. It doesn't conserve angular momentum. It mixes different L's. Okay. Now, I've told you that K2 is the usual K matrix. Maybe you know what that is, maybe you don't. But let's say you don't know. I want to derive a relationship between K2 and M2, the actual scattering amplitude. Okay, the way you do that is in this second step, relating K2 to M2. You look at a slightly different finite volume quantity. It's what we call the finite volume scattering amplitude. And it looks just like we had before, except I get rid of the end caps and I amputate these propagators. And if I sum all the diagrams in my EFT, it's straightforward to show that that leads you to this sum here, where I have just a sequence of beta salpeter kernels. I play the same games. I replace sum with integral plus f cut. That projects on shell. I do similar steps, and I find that this relation, this finite volume scattering amplitude now projected on shell, is given by this expression here. And you notice it's the same denominator. And then the final step is I take L to infinity. I take my box to infinity. But I do so regularizing the integrals with the I epsilon prescription. And if I do that, then by definition, this quantity M2L just goes over to the infinite volume scattering amplitude. What about F? Well, F is a sum integral difference, but the integral is in the PV prescription. So what I get when I take L to infinity is the difference between PV and I epsilon. And that, we all know what that is. That's just a factor of minus I times the phase space. K2 is already an infinite volume. So from this argument, what I learn is the relation between M2 and K2 is this one, which you may recognize as a standard relation between scattering amplitude and a K matrix. So this is an algebraic equation in the two-particle case. But the logic that I've described will carry over to the three-particle case. Okay. I'm not going to say anything about applications. I don't think I have time, but let me tell you that the applications of the two-particle quantization condition are very well developed. People have studied many systems and can pick out resonance poles, all sorts of things. If I had time, I would tell you about recent results on the sigma meson. I've written these slides so that you can read them offline. There's enough data, enough explanations that they're readable. All right, now I want to move to the three-particle formalism. And I am going to skim through this. The basic method of argumentation is the same, but there are a lot of more complicated details. This was originally worked out with Max Hansen in a paper in 2014, and it took us a long time. There was a second paper to finish the second step, and we did it with Feynman diagrams. Later on, with my student Tyler Blanton, we simplified the arguments. I'm just going to sketch it. So the starting point is the same. We have a three-particle correlator. This looks very much like the one I showed you at the beginning for the lattice calculation, except again, I'm in Minkowski time, and I'm looking for poles, and now my kinematic range is restricted to avoid a 5-pion intermediate state. And here's just an example of one of the time-ordered perturbation theory diagrams that will occur in this generic effective field theory. You can have various relevant cuts. Relevant cuts now are 3 particles, and irrelevant cuts have more or less than 3, and they can be replaced by integrals. This builds up a 2-particle beta salpeter kernel, the same one we had before, but now there's a spectator, and you can have a 3-particle beta salpeter kernel too, and you have n caps. So what are the new features that occur? So one is the coordinates that we have. We have 3 particles, not 2. Previously, for a pair, we projected onto L and M in the center of mass. But now we have a third particle, which we call the spectator. So we have to extend our indices to include the finite volume momentum of the third particle. So a big increase in the size of the matrices. The second new feature is that when we do this, we have a sum over K. K is summed. It's in an intermediate loop. As we sum K, eventually this pair here hits threshold. The 3 particles are on shell. But we need to keep going. We need to keep summing K for a while until we're far enough away from the singularity that we can replace sums with integrals. So we need to go sub-threshold, which means that we need, as an input to this, the 2-particle scattering amplitudes below threshold. We can go a certain distance. If we go too far, then we start hitting other singularities, left-hand cuts. And so we can only go a certain distance of order m pi. So we have to put in a cutoff. That cutoff truncates the sum over K, avoids any left-hand cuts in B2, but introduces a cutoff. Another new feature is that we have this switch structure where we go from a spectator over here to a spectator here. That's going to introduce a new type of kinematic function, which we call G, whereas this original one looks like what we had before, except I have a spectator, and that we call F. And we get a new type of kernel, a 3-particle beta salpeter kernel. Okay, so I'm going to skip over all the details. You can organize things into a geometric series by doing some games. You can sum to find the poles. You find that the result, it takes the form of a quantization condition, but it involves a 3-particle K matrix, which is not Lorentz invariant, because we're using time-ordered perturbation theory. It's also not invariant under symmetries under particle exchange. It's not invariant under particle exchange. But then we have found a way of doing a very nasty algebraic reorganization, which makes K3 into a symmetric Lorentz invariant form. I'm not going to talk about that. And we get this final answer, which I showed you before. The quantization condition involves a three-particle K-matrix of some form. And this F3, and what is this F3? It's this thing. And this involves F, which is what I said before, but with the tilde because it has a spectator. G, which involves this switch. So these are kinematic functions. We know what they are. And it also involves K2, the two-particle K-matrix, along with a spectator. So this sort of takes care of all the two-particle interactions, and this adds in the three-particle interaction. And I'm just flashing just to show you that we know how to write down those expressions. So what I flashed you here was the expression for F and the expression for G. Let me talk a bit about what KDF is. So crudely speaking, and this is not precisely true, we have explicit formulae, but crudely speaking, what it is B3 dressed with B2s and higher order B3s. That's the way of thinking about it. Okay, the key properties are, I've already mentioned this, it has the same symmetries as M3, so we can, including Lorentz symmetry, so we can parameterize it incorporating those symmetries. It does not contain exchange singularities. M3, as I'll mention shortly, has divergences in the physical region, as you probably know. KDF does not. That's why it's called divergence 3. It's a real smooth function of momenta, as long as the momenta are real, aside from the possibility of poles associated with three-particle resonances. But it's unphysical because it depends on the cutoff function, which enters into these various integrals. Okay. So what good is it? We need to relate it to M3. We're trying to calculate M3. So we go through a similar story. We define an off-shell three-particle plus two-particle finite volume amplitude, for which we can write down a nice expression. We analyze that in the same way, replace cuts with integrals plus f's or g's. We resum, we project on shell, we play the same game, and we take the L goes to infinity limit. And the result here is a set of integral equations, which I'm not expecting you to take in, but just to show you that we know what they are explicitly, and we can write them out and we can solve them. I just want to summarize what goes into this. So the end result is that M3 is related, it breaks up into two terms, one which I call D and the other MDF3. And what D is this, okay? So this is a ladder sum where we have on-shell two-particle scattering amplitudes connected by an infinite volume version of G. So again, this is well-defined expression, but the key thing is everything is on-shell here. This G enters here, it has a cutoff in it, there's a loop here, so that loop is cut off, but D depends on the cutoff. But this quantity contains all the singularities of the three-particle amplitude. For example, this diagram here leads to a singularity because this intermediate propagator can go on shell. You can have two particles scatter, one of them travel an arbitrary distance before it scatters off the other one, and that leads to an on-shell singularity. That's contained in here. In the case of degenerate particles, there's also a singularity here. The higher terms are not singular, but for non-degenerate, all the terms are non-singular. And the remainder, MDF3, is divergence-free, doesn't have any divergences, and at leading order, it's KDF3, and then it's just higher order expressions. Okay. We've done a bunch of, when we first derived this, we weren't sure it was correct, but we did a bunch of tests. Other people have derived it. It's correct. We've generalized the formalism for three identical particles, and that has been done not only by us in our method, but by two other groups using other methods, and they are consistent. We've basically generalized it to all possibilities, including spinning particles, non-degenerate particles, multiple channels. We know how to do this for almost all systems. So let me, in my remaining 5 minutes, flash for you some examples of how we put this into practice. So the first one I will show you, just to give you an idea of how we do this fitting, a case where we've studied pi plus, k plus. So not 3 pions, but so this is pi plus, k plus goes to pi plus, k plus. So this is a very boring system, but it's a good place to start. The interactions are weakly repulsive. There's no resonances in 2-particle channels or 3-particle channel, but we want to make sure that we can actually do this. So this is a good place to start. So what we do is we get the spectra from lattice QCD for 2 pions, pion plus kaon, and pi k. We parameterize our K matrices. In this particular case, we had 9 or 10 parameters. We included the lowest wave and the next lowest wave, S and P waves. Just to show you, this is from 2 different choices of pion mass, 200 and 340, so we're not at physical in this case. For the lighter of these, this is what the lattice looks like. It's 4 fermi across, 64 cubed by 128, and M pi L is greater than 4. And there are 2,000 configurations. And okay, I'm not expecting you to get a lot from this, but this is the data for our pi k levels on one of the lattices. And along the bottom, they're listed. The number here tells you the total momentum in certain units, and the letter tells you the era. And what you can see, if you blow it up, is that for each level, there's the free energy of pi k, then there's the actual measured energy, and then in teal is our fit. And you can see we fit in total, we're fitting, in this case, 82 levels with 9 parameters, and we get a pretty decent fit. So this is actually non-trivial. We have to use clusters to do this fitting. The orange levels, the threshold where our quantization condition breaks down in this case is because of the Wess-Zumino-Witten term is actually when you add another single pion. So we can't legally go above that, but we can illegally go and see that it still works. We didn't include it in the fit. Okay, and from this, we get results for 2-particle and 3-particle K matrices. And out of that, for example, we can determine the 2-particle scattering lengths, the amplitudes at threshold for pi, k, and k in other calculations. And so we have 2 masses, 6 points. What you can see here is leading order KPT, and next to leading order KPT, they're pretty close. The fit works very well, and it's consistent with the values of low energy constants gotten from phenomenology. So you can see that we can get very good errors on 2-particle scattering quantities here. And given the K matrix, we can go to the scattering amplitude. We have much less good results for the 3-particle K matrices. These are just 2 examples. I won't go into the details, but you can see we have bigger errors. But in some cases, we have evidence that these are non-zero. So let me just move quickly on. The second application I want to talk about very briefly is that we have used chiral perturbation theory to calculate what KDF is for 3 pions, for arbitrary isospin. And so to do this, we joined forces with Hans Beinens and his student and postdoc, because they know how to do one-loop chiral perturbation theory, and we worked in one loop. And we got some nice results. So here's the situation. Forget about the left-hand side. Look at this on the right-hand side. This is the result that we get for one of the terms in the 3-particle K matrix. You can parameterize it as a constant plus something proportional to the total Mandelstam S, and this is the coefficient of S. And you can see in this case we get pretty nice results in terms of statistical error. But this is the leading order chiral perturbation theory that Fernando Romero Lopez and I worked out some time ago, and it fails disastrously. Okay, it's right sort of order of magnitude, but the wrong sign. So this is are we doing something? It's a sanity check. So we calculated the KDF at next to leading order in chiral perturbation theory. It turns out that at that order, the integral equations simplified to just an algebraic form. You have to calculate the one loop in chi-pt, M3, which is what this is, which have been done by these authors. And then you have to do some subtractions, which is non-trivial, but we worked this out. And then you take the real part. And the net result is you get some analytic formulae, which we have, or partially, almost analytic, partially numerical. And what I showed you before was this data here, which disagreed with the leading order KPT. Well, leading order plus next to leading order is this gray curve here. So it turns out there are enormous corrections. So that's good and bad news. The good news is that our disagreement with KPT is resolved in that KPT is not reliable and it has large corrections. The bad news is that KPT is not trustworthy for this quantity. For this quantity, which is the leading order term in KDF, things are better. Again, we disagreed but had the same sign. But we can do a fit to this next to leading order form, which is good. And the correction is large, but not as large. So it's a check that we sort of know what we're doing. And I have 1 minute, which I will use to show you the last thing I want to show you, which is results for the 3 pi plus to 3 pi plus at nearly physical quark masses. So here we're doing the whole story, take levels, determine what KDF is, solve integral equations to get M3. This was first done a few years ago at heavy pion masses. We're now doing it at actually below physical pion masses. And we have to have a bigger lattice in order to keep M pi L is 4. And this is sort of state-of-the-art lattice, 100 cubed by 200, with a small lattice spacing. Okay, I'm just going to show you the results of this process. First of all, this is what the two pion amplitude looks like. This curve here is the real part of the S-wave amplitude, and the blue is the imaginary part. This is threshold. I'm showing it versus the center of mass energy squared over m pi squared. So this is threshold. As I said, we need to have it below threshold, and this is what we have. We get from our fit, and we have a cutoff which cuts it off, left-hand cut, and there's the Adler zero that was mentioned this morning. So we find the Adler zero. We also have results, which you can see out here for the D-wave interaction, but they have much bigger errors and are tiny. So they play a very small role. And then finally, this is the ending thing, last thing I want to show you. These are our results for the 3-particle 3 pi to 3 pi scattering amplitude, which is a function of 8 kinematic variables. So I have to make some slices here. So one thing is I projected it onto overall 0 minus, and then I've chosen a configuration where the 3 particles have the same, are in the equilateral triangle with the same momenta, same magnitude of momenta, same energy, and plotted against the center of mass energy as I scale up these triangles. The relative axis between these two doesn't matter for this channel. And what you see here is the real and imaginary part. And okay, like as was discussed previously, it's a kind of boring curve. We've done it. We've got a result for 3 pion to 3 pion scattering with essentially physical quarks in the simplest case of 3 pi pluses. Notice it's diverging. It does diverge at threshold. That's the divergence I was talking about. This on the right is the MDF, the part which is proportional to KDF. And you can see this is consistent with 0 in the 3 pion case, which is exactly what we expect. For using KPT, this should be very small, and we find it to be very small. So this is just to show you we can do it. Okay, so that's the end of my slides. I just want to very briefly summarize. And I'll just read the blue things, and you can read the rest at your leisure. So the 2-particle sector, it's really in a precision phase. Major steps have been taken in the 3-particle sector. We have some actual results. We're working on implementing this in many different systems, 3 pions with other isospin, the Roper system, nucleons plus pions, the doubly charmed tetraquark. We want to complete the formalism. There's a few steps to go. And then with the idea of D to KK bar and pi plus pi minus and 4 pions and so on in mind, we want to go to more particles. Thank you.
Thank you very much for a very nice talk. Any questions for Stephen?
I think there are conceptual problems with your calculation. The bound states like pions, for example, they involve infinite tower of correlated partons. And in your effective field theory, you truncate it. So what you're doing at best is resumming only parts of this series.
You're talking about higher particles?
Well, I'm talking about higher correlated states of the partons inside the bound state. And of course, the
Right. But those are at higher energy, and we can integrate those out, and they just become contributions to the vertices in our effective theory. They don't contribute to any intermediate on-shell states, and that's all we care about in this analysis.
Well, they do contribute. Even inside the bound states themselves, there is a lot of contribution. Just think about the proton mass that's coming from this virtual gluons from the vacuum. And of course, they contribute to the scattering amplitude.
Right,
You're
but
only taking part of that.
no. We have everything in there. But that comes from the calculation of the. So we're expressing things in terms of infinite volume quantities. Those infinite volume quantities have all those contributions in there, I would claim. We can discuss more.
Lance?
Thanks for a nice talk, Steve. I was curious whether any of these techniques could help shed light on the discrepancy between the dispersive and the lattice evaluation of HVP, since you have rhos and omegas in there. Of course, it's pretty precise, a lot of precision's needed, so maybe it's tough.
Maybe eventually. I don't
Okay.
really have anything
It's a
to say
ways
now.
out. Okay,
Yeah.
Thanks.
This one up the back.
Julio?
Yeah, two quick questions. So
Yes.
for the 3-pion amplitude, there should also be an Adler zero when you take the center mass energy of two of the pions, small. Can you see that in your data?
Not so far, no.
Okay, and then about the disagreement with Carroll perturbation here.
Yes.
Were these calculations in the Carroll limit or with like actual like close to real quark mass?
Well, we have it as a function of quark mass. So
So even at small quark masses,
well, it's small enough quark masses, then it's okay. I mean, if you just look at this, if you go, down here, really small quark masses, then the corrections are small.
okay.
Yeah.
Thanks.
We're a little bit behind schedule, so unless there is a really quick question, let's thank Stephen again.